This is Chapter 8 on complex numbers and polar equations, and we will not go over parametric equations in this class. Section 8.1 is on complex numbers, and hopefully this is a review for you. The basic concepts: the imaginary unit I is equal to the square root of -1, and I squared is equal to -1. A complex number can be written as a plus bi so this is a complex number. In the complex number a plus bi, a is the real part and b is the imaginary part. I'm using different colored ink just to make it more interesting for this section. The equality of complex numbers a plus bi is the same as c plus di if the real parts are the same and the imaginary parts are the same. If b is equal to 0, then a plus bi is just a, which is a real number. So an example, 2 is a real number. We could write this also as 2 plus 0i. That's a real number. If b is not equal to 0, then a plus bi, there's an extra a here, you could just cross that off. A plus bi is a non-real complex number. An example, if we have the square root of 5 minus 3i. It's not real because you have an imaginary part, and it's a complex number. It can be written in the form a plus bi. If a is equal to 0 and b is not equal to 0, then the non-real complex number is a pure imaginary number. So all of these are complex numbers, and a or b could be 0. If b is not 0, an example is if we have 2i, that's a pure imaginary number, and we could write this as 0 plus 2i, so either way. And if you write the number in the form a plus bi, it is in standard form. In the case where you would want to write a plus ib, if you have something like 7 plus I root 2, you normally put the root after the I to make it more readable because that I has to be outside of the radical. You go to the top of the next page, 8-2, you can see the relationships between all the numbers. The natural numbers are numbers that you can count with your fingers. The whole numbers include all the natural numbers and 0. The integers include all the whole numbers and negative numbers, so positive and negative whole numbers. Rational numbers are fractions, like the integers, you can just put those over 1. Those are all rational. And then the irrational numbers are numbers that are messy when you put them in your calculator. You'll get a decimal form that's not repeating and not terminating. And then the rational numbers and the irrational numbers make up the real numbers. The complex numbers, that's all of these, are made up of real numbers and pure imaginary numbers, and then combinations of them. The meaning of the square root of -a, whenever you have a negative under the radical, you can take that out. So this is like the square root of -1 times a. That -1 comes out as I. At the bottom of page 8-3, it says operations on complex numbers. Here, whenever you're working with taking out a negative from the radical, you want to make sure you do that before you do any other operations. Let's look at the reflection problem. If you have the square root of -4 times the square root of -100, you cannot do this. You can only combine radicals if you have real numbers, not if you have imaginary numbers. So this does not work. and I'll let you figure out what this would be if you simplify it. You have to take out the negatives first, and those become I, and then you'll see that you're going to get a different answer than 20. Let's skip the next page. Those are examples. Going on to 8-5. When you're adding and subtracting complex numbers, it's pretty simple. I think it's easier if we just go here to the words. That is, to add or subtract complex numbers, add or subtract the real parts and add or subtract the imaginary parts. You can think of this as combining like terms when you're adding and subtracting complex numbers. When you're multiplying complex numbers, I think it's easier, instead of thinking of it this way, is just to use the FOIL method. So when you're multiplying, use the FOIL method, and then you can think of it as combining like terms, and then don't forget that I squared is equal to -1 for that last step when you're simplifying. The next page, page 8-6, two complex numbers that differ only in the sign of their imaginary parts are called complex conjugates. The product of a complex number and its conjugate is always a real number. The property of complex conjugates: whenever you multiply a number by its conjugate, do you see how the I will go away? You're squaring the first term, and you're squaring the last term without the I, and a plus in between. To find the quotient of two complex numbers in standard form, we multiply both the numerator and denominator by the complex conjugate of the denominator. Let's go down to the powers of I. Let's see if we can find a pattern when we're taking powers of I. I to the first power is just I, and we know I squared is -1. I cubed is the same thing as I squared times I, because if you add the exponents, 2 plus 1 is 3. Replacing the I square with -1, we have -1 times I, which is -I. I to the fourth is I squared times I squared, and we know I squared is equal to -1, so replace those with -1, and then we get 1. I to the fifth, starting with I to the fifth, we can write this as I to the fourth times something. This is going to be I to the fourth times I to the first, because 4 plus 1 is 5. I to the fourth is 1, we found that here, times I, which is I. We can write I to the sixth as I to the fourth times I squared. So we add the exponents when we're multiplying the bases. I to the fourth is 1, and then I squared is -1. So that's -1. I to the seventh is I to the fourth times I cubed. I to the fourth is 1. We found that I cubed is -I, so this is -I. I to the eighth is I to the fourth times I to the fourth. Well, I to the fourth is 1, so we have 1 times 1, which is 1, and so on. Do you see the pattern? Powers of I cycle through the same 4 outcomes. They start off with I, and then -1, and then -I, and then 1. Because I to the fourth has the same multiplicative property as 1, it follows that a power of I with an exponent that is a multiple of 4 has a value 1.